Welcome to Study Loop.
Hello everyone, today we're doing chapter 14, problem 16. And this problem asks us how many peaks are present in the NMR signal of each of the indicated protons. So the question has some arrows pointed to which protons it's interested in, but I just drew them in blue for this question. And the very last one is interested in all protons in the question, in the molecule. So these are in black. So let's start with the most left one, that being A. So we're only interested in this blue proton here. And if you remember, there's two rules we need to consider. So the number one is the splitting pattern for your proton is equal to your number of neighboring protons plus 1. But now, what happens if you have two neighboring protons that are chemically unique from one another? So if you have one neighboring proton that's different from the other neighboring proton, then you have a kind of modified rule, being that your splitting pattern equals the number of neighboring protons from your adjacent carbon A, plus 1, and that's multiplied by the number of neighboring protons from your adjacent carbon B, so your other adjacent carbon, plus 1. So we'll see when this second formula comes in handy, but let's start with A. So in A, we're interested only in this blue proton here, and we see that this blue proton is bounded to a central atom here, and it's neighboring several things. So it's neighboring this terminal methyl group. So this methyl group has 3 protons, and also the central carbon with this blue proton of interest is also neighboring this methyl group that has 3 protons. But then also the central carbon is bounded to this carbonyl carbon, but this carbonyl carbon has 0 neighboring protons. So we have to ask ourselves, are these two neighboring protons identical or different? If they're identical, we use the first equation. If they're different from each other, then we have to use a second equation. But these are identical because they're both methyl groups. So here we have 6 neighboring protons plus 1. So we will have 7 peaks for this single 1 proton here. Now let's look at the second problem here. So the second problem, let's identify the unique proton. So we have a terminal group here, and then we have this CH2 here, and another CH2 here. So there's no internal plane of symmetry in this molecule, and if you see here that this CH2 is bounded to a terminal methyl group and then a propyl group, while this CH2 on the right is bounded to an ethyl group and another ethyl group. So what you have essentially is 2 unique chemically distinct protons here. So now let's look at the blue protons. So the blue protons, let's determine the splitting pattern, number of peaks here. So the blue protons, we're interested in these 3 protons, how would they look in the chemical NMR spectra. So these 3 protons are bound to a central carbon, which is neighboring this CH2 here. The CH2 has, like it mentioned, 2 protons. So you have 2 neighboring plus 1. So you have 2 plus 1 to give you 3 peaks for these 3 protons here. And now let's look at these protons here. So these protons at the very end, the red protons. So these red protons, remember, these red protons are adjacent to this CH2 here, and also this CH2 here, but this proton here, if you see, we have 1, 2, 3, 4, 5 protons. This is exactly in the middle of this molecule. So this CH2 on the right side is identical to the CH2 on the left side. So in essence, we have the same adjacent protons on either side of this molecule, so we can still use the first equation here. So we have 4 neighboring protons plus 1, which gives us 5 peaks for these red protons. But now here's where the interesting case comes in. So I saved this for the last, so now this green proton here. So this green proton we have is bound to the central carbon, and the central carbon is bound to 2 adjacent carbons, one being this terminal methyl group on the left, one being the CH2 bond on the right. So obviously this terminal methyl and the CH2 are different types of protons. So this is a terminal methyl, 3 protons. This is CH2, 2 protons, which is also adjacent to another CH2, CH3 bond here. So these are 2 unique neighbors. So for this case, to determine these green protons, we have to use equation number 2. So let's call the left side neighbor A and the right side neighbor B. So neighbor A, we have 3 protons, and if you do the plus 1, that gives us A. Now we have to times this by B. So in neighbor B, we have 2 protons here in the red plus 1. So our splitting pattern is going to be 4 times 2 times, 3, 2 plus 1. So that equals 12 peak maximum number of protons. But in essence, because this is a flexible alkyl chain, the signal of these 2 green protons can overlap. So these 12 peaks will most likely overlap. So in essence, you will just see something that resembles the equation 1. So you have a total of 3 plus 2, so you have 5 neighboring protons plus 1. So you most likely will actually see 6 visible peaks. You'll most likely see 6 visible peaks, even though 12 is the maximum number of peaks. But some of these will overlap because of the flexible nature of this molecule. So in essence, you'll most likely only see these 6 peaks. Now let's move over to this problem here. So this problem, we have 2 unique protons. So this proton is bounded to the carbon that's bounded to the chlorine, while the proton on the right is bounded to the carbon that's adjacent to the bromine and is trans to the chlorine. So we have 2 unique protons here. Let's look at A for the splitting pattern. So A is bound to a carbon, that's bound to a chlorine with no protons, and it's also bound to a carbon here that's bounded to 1 proton. So we have a total of 1 neighboring protons for this blue proton here. We have 1 neighboring proton plus 1, so that'll give us a doublet. So we'll have 2 peaks here. But now let's look at the green protons here. So the green protons, we're bounded to a neighbor here that has 1 proton, but we're also bounded to a carbon here that has 2 protons. So this carbon with these 2 protons, these are unique because they are first cis to both of these electronegative groups, and this carbon is directly bounded to the electronegative bromine. So this neighbor green is different from this neighbor blue. So we have to use the bottom equation. So if I call blue A and green B, I see that to determine the peak pattern of this green proton, I need to look at this neighbor A, which has neighboring 1 proton plus 1, and you have to multiply that by neighbor B, which has 2 protons off this carbon plus 1. So I have a totals for splitting pattern 2 times 3, so I will have 6 peaks for this green proton here. And now let's look at the 3 protons on this molecule here. So we see that this proton is directly bound to the carbon that's bound to the bromine, while this proton here is trans from the bromine, while this proton on the bottom is cis to the bromine. So if you recall, the blue one is bound to the same carbon as the bromine, the green is trans to the bromine, and the red is cis to the bromine. So now we have 3 unique chemical environments. So they're all unique protons, so they all give us different signals. Not only that, because we know all 3 of these are unique protons, that means that they will all cause different neighboring splitting for each other. So for example, if we're investigating the red proton here, its neighbor of this proton here is unique to its blue neighbor here. So what you see here is that if I'm investigating the red one here, if I call green A and blue B, I see that this carbon here is directly bound to one neighbor plus one, but then it has another neighbor here that is a unique proton. So I'm going to multiply that by a new unique proton neighbor plus one. So that gives me 2 times 2. So I'm going to have a 4 peaks splitting pattern for this red proton here. Similarly, if I'm investigating this green proton here, I see that green proton has a neighbor A and a neighbor B that's different from each other. So once again, we have one neighbor A, which is 1 plus 1, times that by one neighbor B, one neighbor plus 1. So once again, I have 4 peaks for proton green. And now if I'm investigating this proton here, B, we see that now we have one neighbor here and one neighbor here. So with these two neighbors, once again, if I were to call this A and B, we have one A neighbor, so we do 1 plus 1, and we have one B neighbor, so that's 1 plus 1. So that also equals 4 peaks. So in essence, these 3 protons will be represented by 4 unique quartets on our NMR spectra.